So what is the capacitance of a parallel plate capacitor? Of course, you could just take the definition of capacitance as the charge on the capacitor per unit potential difference, but let's try to find the capacitance just in terms of the properties of the capacitor. The way we'll do this is by finding an expression for the potential difference using the definition of potential difference as the path integral of the electric field, and we'll find the electric field using Gauss's law. So what's the electric field inside a capacitor? By leveraging the principle of superposition, we know that it will just be the sum of the field from two uniformly charged plates. Let's choose a prism-shaped Gaussian surface, a cylinder specifically, because from the symmetry of the system, the electric field is the same at the same distance from the plate, and the field will be parallel to the normal vector of the surface. We'll also define sigma as the area charge density, Q over A, where Q is the total charge. With that, we can pull the magnitude of the electric field out of the integral and integrate over the surface, giving the area 2 pi r squared for the two circles, since the normal vector on the sides of the circle are at 90 degrees to the field, and cosine 90 is 0, so that part of the integral drops out. On the right-hand side, we can change the charge enclosed to sigma times pi r squared, because the cylinder is enclosing a circle on the plate. Then we can cancel out pi r squared on both sides and rearrange for the electric field as sigma over 2 epsilon naught. Returning to the capacitor, because one plate is positively charged and the other is negatively charged, between the plates the field adds to sigma over epsilon naught. It's important to see that this is a constant for our next step. The potential difference is simply the integral of the electric field over a path. So if we choose our ds to face straight down, then we can pull out the electric field, and the integral is just the length of the capacitor, which we'll call d. So the potential difference is sigma over epsilon naught times d. We're now almost done. Just sub that potential difference into the definition of the capacitance, and notice that we still have a sigma and a q, which we don't want. But the total charge q is just sigma times the area of the plate. So the sigmas cancel out on the numerator and the denominator, and we're left with the formula. This is a remarkable result because it means that the capacitance in this admittedly idealized scenario depends only on the geometry of the capacitor. An important note is that this assumes the dielectric is a vacuum, and you'd need to add another constant to deal with the changes to the field caused by a different material. For more on capacitors, you can check out my derivation of the discharge equations, or you could also check out some of my other videos. Thanks for watching, and bye-bye.